Okay, in last lecture we have discussed about designing of IR filters and we have gone through two approaches uses mapping between Laplace transform to jet transform, and we have also discussed the transfer functions in three cases for analog filter. So today we will discuss our first topic for IR filter design is IIR design by approximation of derivatives. This particular relation we have seen in our previous lecture between input and output in time domain. So a differential equation can be converted into a difference equation so our target is we have a differential equation and we have to represent that differential equation in difference equation. So let's say we have a system which is analog differentiator. So we provide input xt, so output we got is yt. Then yt will be equal to del xt over dt. Then taking Laplacian transform, we get ys equals to s xs minus xc. We assuming system is relaxed before applying an input, will give x0 is equal to 0 and ys will be equal to s. Then ys by xs will be equal to s, and that is equal to nothing but transfer function of hs. So we have obtained the analog domain transformation, that is hs is equal to xs. Now if we sample input and output at t is equal to nt, then input is xt, output is yt, and we know the relation yt equal to del of xt by del t. Now we want to sample at t is equal to nt, and we want to sample again at t is equal to nt. Then this will be equal to y nt equals to, now by using the definition of differentiation, del xt by del t indicates a smallest change from one point to another point. Now if t is equal to nt, the smallest change will be from one sample to another sample. So we can write this as x nt minus x nt minus t over t, and we can write ynt as yn and xnt as xn will give yn equals to xn minus xn minus 1. Now, if we take the Z transform of the equation, will give yz equals to xz minus z inverse xz by t. If we write again this equation as yz equals to 1 minus z inverse into xz by t, that's mean hz is equal to yz over xz equals to 1 minus z inverse by t. For a better sequence between Z transform and Laplacian transform, we will write this Hs as HAS when for analog domain. Now, for the mapping between analog and digital filter, HAS should equal to Hz. That means mod of HAS should equal to Hz. That means S should be equal to 1 minus Z inverse by T. Now we have obtained a relationship between S and Z. Now, to verify this particular case, we can, for further verification, we can increase the order of differentiation, and that will give for second order by t is equal to del square xt by dt square, and at t is equal to nt, and at t is equal to nt, it will be can be written as del by del t and del xt by del t at t is equal to nt. Now we can write yt at t is equal to nt will be equal to del by del t, and it is x and t minus x and t minus t over t. So it is yn equals to ynt equals to del by del t of x and t will give x and t minus x and t minus t, then minus sign x and t minus t, so this is in bracket, minus x and t minus 2t, this is whole under t. So this is by t, and this expression is also divided by t. Then we can write yn in terms of yn is xn minus 1 by t minus xn minus 1 minus xn minus 2 by t over t. Then yn can be written as xn minus 2xn minus 1 plus xn minus 2 over t square. So if we take Z transform of this, of the equation, it will give yz equals to xz minus 2z inverse xz plus z minus 2 xz over t square. Then taking xz common, so it is yz by xz will be equal to 1 plus z minus 2 minus 2 z minus 1 by t square. So if we see this yz by xz is nothing but 1 minus z inverse by t square, and that is equal to hz. Now for any derivative for the kth derivative, hz will be equal to yz over xz 1 minus z inverse by t to the power. Now finding the equivalent HAS, as we know for second order, as we have started from second order, so yt is equal to del square xt by del t square. So taking Laplacian transform, ys will be equal to s square x, and we are not writing that initial condition, so that will be 0. So ys will be equal to s square xs, and it can be written as ys over xs equals to s square will be equal to hs. That's mean comparing analog and digital part, we get s square is equal to 1 minus z inverse by t whole square. For kth order, s to the power k will be equal to 1 minus z inverse by t to the power. Now from this discussion, we can write hz is equal to has for s is equal to 1 minus z inverse by t. Now we have applied the derivative part to find out the relation between z and s, and now we will see the mapping between z and s. So for that we can write s is equal to 1 minus z inverse by t, and we can solve this equation. So it will get s is equal to z minus 1 by zt, and this sz will be equal to z minus 1. So we can take z common, and it will be 1 minus st equals to 1. So z will be equal to 1 over 1 minus st. Now we know s is equal to sigma plus j omega. So at the imaginary axis, we want to analyze as this axis will define the existence of a Fourier transform. So that's why we'll put sigma tends to 0. So S will be j omega. Then Z will be equal to 1 over 1 minus j omega t. Now we can multiply 1 plus j omega t and 1 plus j omega t. Then this equation will be 1 plus j omega t over 1 plus omega square t square can be written as in the form of x plus jy will be equal to 1 over 1 plus omega square t square plus j omega t over 1 plus omega square t square. Now we want to find the result for varying omega, as omega varies from minus infinity to infinity, and we want to map that particular result in z domain. So at omega is equal to minus infinity, so we have z equals to 1 over 1 plus omega square t square plus j omega t over 1 plus omega square t square at omega is equal to minus infinity. So this will give 1 by minus infinity will be 0 plus j infinity by infinity. So this is problem to be handled by L hospital rule. Then it will be equal to 0 plus j t over infinity, that is minus infinity, and this relation will be 0 plus j0 will be equal to 0. So z at omega is equal to minus infinity is equal to 0. Now second case, at omega is equal to 0, that means z at omega is equal to 0 will be equal to 1 upon 1 plus omega square t square plus j omega t over 1 plus omega square t square at omega is equal to 0. Substitute omega is equal to 0, it will be 1 plus j 0. So z at omega is equal to 0 will be equal to 1. Now point third is at omega equals to infinity, we know z at omega is equal to infinity will be equal to 1 upon 1 plus omega square t square plus j omega t over 1 plus omega square t square at omega equals to infinity. Now if you substitute this relation, so it will be 0 plus j infinity by infinity. So using L'Hospital rule to avoid this condition, will give zero plus j t by infinity, which is equal to 0. So that is z at omega is equal to infinity is equal to 0. Now what does it means? So in S plane we are having a j omega axis, and this is the sigma. So we have points through this j omega axis from minus infinity to infinity. It is going towards infinity from minus 1. Then we have z plane, which is in this case is imaginary z. Here it is real z, and then we have a unit circle. So it is minus 1, this is 1, and in this case it is mod z equals to 1, right? So what does it means is minus infinity is mapped to point 0. So we start from point 0, and point 0 is mapped to point 1. That's mean this whole section from 0 to minus infinity, or we can say from minus infinity to 0, is mapped between 0 to 1, but in negative part. Okay. Now this infinity is also mapped to 0. That's mean then this mapping starts like this and goes to 0 again. Okay. So the mapping of all frequencies from minus infinity to plus infinity mapped at the circumference of this circle with diameter 1. So that's mean its radius is 1 by 2. Center point is 1 by 2. Now all the poles which are lying at the left hand plane, this is LHP, this is RHP, lying at the left hand plane are mapped inside this circle. Then only this particular system will be stable, because this circle inside this unit circle, all the frequencies are mapped at the circumference of this circle, and all the poles which are located at the left hand plane are mapped inside this circle. So this is the mapping between S and Z by using derivative approximation. Locus of the points in Z domain will vary only from 0 to 1. All the poles in left hand plane of S plane are mapped inside the circle from 0 to 1 with radius 1 by 2. That means this mapping is restricted only for the low frequencies. And point is, this kind of transformation is only suitable for low pass filters and band pass filters, but with very small resonant frequency. That's all for this lecture. Thank you.